Hi everyone, Mr. Chu over here. Today I will go through this law, very important law in advanced magnetic field syllabus, which is called the Ampere's law. Now the Ampere's law form is given as this, is written in this form, which is mu naught integral of B dot dl is mu naught I. So what is meant by this law over here? What does this B dot dl means, and what is this mu naught I? First of all, let's start off with the easiest one. Mu naught is what we call the permeability of free space. It basically describes the ability of magnetic field to exist in a certain material. So in say iron, it will have a very high value, and in free space, this is mu naught. In iron, it will be multiplied by another relative permeability. So let's assume that everything is in free space. So what is this B dot dl? What it means is that if I got a current over here, if I were to choose an Amperian loop, now it sounds really scary. Remember the last time we talked about Gaussian surface? Gaussian surface is that we choose a surface that encloses a charge. So what we have over here is a surface, that's Y is E dot ds. So it's the E field coming out through the small little area ds, and we talk about area having a vector which is normal to the area. So B dot dl, we talk about loops. Over here is loops rather than an area. Okay, so for the Ampere's law, we talk about loop. So say for example, if we choose a loop like this, it doesn't matter which loop you choose. The reason why we choose the loop this way is because the field, the magnetic field due to the current, is actually a uniform of uniform value at all points around this dotted line over here, because it's the same distance away from the current. So we also know that it's kind of like working backwards. We also know that the field is circular by nature. So this B dot dl is actually the magnetic field over here. We know that it is like this. Dot product, we learned about dot product in the past. It is actually B dl cos theta. The cos theta being the angle between the field and the loop direction. So if we choose the loop direction to be the same direction as the field, then this will be, theta will be 0, and therefore this one will be, cos theta will be 1. So B dot dl becomes B dl. So in this case, it will become B dl equals to mu naught I. Now what is this I over here? Mu naught is a constant. I is the current enclosed by this surface, which in this case, the current enclosed by the surface is just I. It may not be I in other examples that I'll show you later. So in this case, B is constant throughout this whole loop. So we bring B out, and it becomes integral of dl mu naught I. And you can see that if you integrate dl, it will simply be, so there shouldn't be d dl. If you integrate dl, it should be simply L, which is the length of the loop, which is b 2 pi r being the distance from here to here, is the radius of the loop that you choose. So the magnetic field is equal to mu naught I upon 2 pi r. And this is the equation that I would recommend you to remember as a good physics student. Not in the IB syllabus, but it's always good for you to remember these basic equations that governs the relationship between magnetic field and the distance of that point that you're interested in away from the current. Very basic and important equation. And it is how you can derive the expression for the magnetic field of a wire of current carrying conductor from the current carrying conductor using the Ampere's law. So I've shown you how you can decide what is I, that is the current enclosed or cut by the surface area over here of the loop. And B dot dl, I've shown you that by choosing the correct loop, it can simplify things a lot, just like a Gaussian surface. If you choose the area, the surface where the E is constant throughout, you can bring the E out, just like how I brought the B out over here. Let's try this law on another scenario, which is what we learned today. So let's take a look. Or rather yesterday, by the time you watch the video, it will be tomorrow. So what we learned today, which is the field due to a loop. Now let's choose the Ampere loop such that it goes in here and like this. Now remember that the field lines go this way, this way, this way, and the field goes this way. But if the loop is infinitely long, it will never come back. Alright, if it is infinitely long, it doesn't come back. So we're talking about an infinitely long solenoid, not a solenoid that is of finite length. So if you have a infinitely long solenoid, there's no field bending back. Now if you take B dot dl equals to mu naught I enclosed. Now this I enclosed will be n times the I that it encloses. So if this loop over here encloses 10 currents that passes through like this, it will be 10 times the current in each of the loop. So you actually multiply the number of turns that it encloses. Now B dot dl, let's take a look. We have 4 sections over here. So let's call this A, B, C, and D. So therefore it will be B dot dl AB plus B dot dl BC plus B dot dl CD plus B dot dl dA. Now take a look at the direction of the field and the loop direction. Whether it goes here or here, it doesn't matter, the angle is 90 degrees. So remember, coming back to here, dot product is cosine theta, so it is cosine 90. And cosine 90 is 0, so anything that goes here and here will be 0. Therefore, BC and CD goes to 0. Next, I said that it is an infinitely long loop, so the field over here is 0, so B over here is 0. Therefore, this whole integral becomes B over here times the length of the Ampere loop over here equals to mu naught n I. So B is simply equals to mu naught n upon Li, which is mu naught n I. Now do be careful, this equation over here, the n over here, I intentionally chose that it is not the same as the big N. The big N is the number of loops, whereas the small n is the number of loops per unit length. So if I got 400 turns in 50 centimeters, the n that you substitute over here must be 800. 400 in 50 centimeters, the n is 800 turns per meter. So you must be very mindful that this is number of turns per unit length. Okay, and this is how I can apply Ampere's law again into this scenario. Alright, now I'm going to show you how I can apply this to 2 other scenarios that gives very interesting results. Now, what if I were to go inside a current? What do you mean? How do you go inside a current? So say for example, if you got a very big current loop that goes this way, say this is a big wire and the current flows evenly distributed in this whole area. This is big R, and I'd like you to find the field at this point. At the distance small r away from the center, well, the conductor has a radius of big R. Now, first of all, let's quote Ampere's law again, mu naught I enclosed. And let's choose an Ampere loop that passes through the point that you want to find the field. The loop is a circular loop with a radius R. So the field at that point over here, all those points over there should be constant, so I can bring this out and integral dl is just 2 pi r. Mu naught I enclosed is equals to I over pi r squared times pi r squared, which therefore, if you work it out, B is equals to mu naught, this cancels out, I r squared upon 2 pi r squared r, which is mu naught I r upon 2 pi r squared. So the B actually increases uniformly with small r. Now when small r equals to big R, can you see that it will be mu naught I upon 2 pi r, which is what we got just now. So this is a very classic case of Ampere's law being applied to within a conductor. Okay, just remember the rule, B dot dl integral, sum up all the B dot dl across the whole thing. Usually we choose a loop where the B is constant, and then equals to mu naught I enclosed. And the I enclosed by the surface over here, which is the current divided by the whole area times the area of the small loop itself. Now the last example I'm going to show you is very interesting. It's linked back to what we learned about the charged plate's electric field. Let's take a look at this. It's actually a step to a major discovery in the past by Maxwell. So let's imagine two electrical plates. So if we were to apply, if there is a current flowing here, and I choose an Ampere loop. Now remember that the current mu naught B dl is equals to mu naught I enclosed. Now this is the interesting part. Now can you see that this mu naught I enclosed, most of the time we talk about this area. What if we choose the area to be this? Just now we talk about this area, therefore the I enclosed is just I. That's the usual way that I've been using for the past 3 examples. But what if I choose the area here? What is the current enclosed by this area? 0. Then your B dot dl will be equals to 0, but we know that B dot dl across this loop over here is not 0. So how do we reconcile this problem? Now this is the interesting part. Remember that if you've got a charged plate, the E field, we derive it using Gauss' law that the E field, the electric field, is equals to rho times mu naught epsilon naught. And therefore, can you see that dE dt is equals to d rho dt divided by epsilon naught, which means that d rho dt, which is equals to something that I'll talk about later on, is equals to E naught dt, E naught epsilon naught dE dt. Now can you see that this is the rate of change of charge density, which is actually the rate of change of charge stored on the plate, which isn't it current? This is very spooky. If you actually talk about a change in electric field, it is equivalent to a current. The change, there is no current flowing here, right? But the change in electric field is equivalent to a current. And this is the missing piece inside Ampere's law. Ampere's law was not complete. So therefore, they added a correction factor, which is what we call now as the displacement current. And therefore, this becomes the complete form of Ampere's law now. Now this addition of mu epsilon naught dE dt has huge implication, and it is basically the basis on which Maxwell derived the equation that governs the speed of light, that tells us what's the speed of light. The equation, the derivation is very mathematical, but this is the basis from which it can be derived. And it can be derived as C is equals to 1 on square root mu naught epsilon naught. What you can do if you're interested in the math, you can actually search Google Maxwell equation derivation of speed of light. You will find that it starts with this displacement current, because that's the fundamentals. And then from there, that's where the derivation comes about. It links electric field and magnetic field, if you notice. And that's the one that beautifully links a changing electric field with time to a magnetic field that is across a loop. What we learned in Faraday's law is that if you have a changing magnetic field, it relates to an electric field that results in an EMF. Whereas this one, a changing electric field with time induces a magnetic field. So it becomes co-inducing. Yeah, a changing electric field induces a changing magnetic field, induces a changing electric field, and that's where we have a electromagnetic wave. Alright, so enjoy, have a nice day ahead, and hopefully this lesson gives you a dipstick experience and knowledge about what Ampere's law is. And we have done Gauss' law. The next one that we'll do in a series of advanced electromagnetic field is what we call Biot-Savart law. Yes, what you call the BS law. Alright, thank you, bye-bye.